New on CuriosityStream. How do you connect a 16th century potato to limitless energy production? Could Napoleon's toothpick have a direct link to a machine that predicts the future? And how can a 1700s conch shell chart a course to humans connecting their brains to the internet? James Burke's visionary series Connections returns for a new generation. Experience all new Connections. With monthly, annual, and bundled plans, find the one that works for you at curiositystream.com.
Hello, saver. Whether you're saving for that trip to the tropics or saving for an emergency, now is the time to take advantage of Wells Fargo's savings options. Wells Fargo offers savings accounts that can help you save towards your goals. So, what are you saving for? Visit a Wells Fargo branch or wellsfargo.com/save to open a savings account today.
Wells Fargo Bank, N.A., member FDIC.
This is SpaceTime, Series 23, Episode 125, for broadcast on the 23rd of November 2020. Coming up on SpaceTime, the brightest kilonova ever seen, a new way of seeing invisible dark matter, and a record close shave as another asteroid skims past the Earth. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have detected the brightest kilonova ever seen, unleashing more energy in half a second than the Sun will produce over its entire 12 billion year lifespan. The massive blast, known as a short gamma-ray burst, is thought to have been caused by the merger of two neutron stars to produce a magnetar, a rapidly spinning neutron star that has large magnetic fields, dumping huge amounts of energy into the surrounding environment and creating the very bright glow seen. Gamma-ray bursts are the most energetic explosive events in the known universe after the Big Bang of creation. They're split into two basic classes based on the duration of their gamma rays. If the gamma-ray emissions last longer than 2 seconds, they're referred to as long gamma-ray bursts. These events are known to result directly from the core collapse of a massive star in a Type II supernova event. On the other hand, if the gamma-ray burst lasts less than 2 seconds, it's considered a short-period burst. And these are thought to be caused by the merger of two neutron stars, resulting in the creation of a stellar mass black hole. Neutron stars are the superdense stellar remnants of stars far more massive than the Sun, which have exploded in powerful core collapse supernovae at the end of their lives. When they run out of nuclear fuel and their core fusion process ceases, the balancing act between the inwards pull of gravity and the outwards push of nuclear fusion also ceases, and gravity wins. This causes the progenitor star to suddenly collapse in on itself with so much force it pushes through what's known as electron degeneracy, the barrier which prevents neutrons and electrons and protons from all crushing together. And once they push through this electron degeneracy barrier, the positively charged protons and the negatively charged electrons in the core are crushed together, forming neutrons, hence the star's name. The end result is an object with more mass than the Sun, but crushed down to the size of a city. This material is so dense, just a teaspoon of it would weigh literally billions upon billions of tons. Kilonovae are an optical and infrared glow from the radioactive decay of heavy elements, and they're unique to either the mergers of two neutron stars or the merger of a neutron star and a stellar mass black hole. The burst, reported in the Astrophysical Journal, first arrived on May the 22nd this year as a blast of gamma rays detected by NASA's Swift Space Telescope. Astronomers also examined it in optical, X-ray, near-infrared and radio wavelengths using NASA's Hubble Space Telescope, the Very Large Array Radio Telescope in New Mexico, the 10-meter Keck Observatory in Hawaii, and the Los Cambrias Observatory Global Telescope Network. These allowed them to study the explosion's aftermath and its host galaxy. The intense flashes of gamma rays from these bursts appear to come from jets of material travelling at almost the speed of light. Now, these jets don't contain a lot of mass, maybe just a millionth the mass of our Sun. But because they're travelling so fast, they release a tremendous amount of energy in all wavelengths right across the electromagnetic spectrum. And this particular gamma-ray burst was one of the rare instances in which scientists were able to detect light right across the electromagnetic spectrum. Surprisingly, compared to the X-ray and radio observations, the near-infrared emissions detected by Hubble were some 10 times brighter than expected. Hubble was able to take its image only 3 days after the initial burst, and through a series of later images, Hubble showed that the source of the burst had faded in the aftermath of the explosion. Using the Keck Observatory's low-resolution imaging spectrograph and deep imaging multi-object spectrograph, the authors determined the burst must have come from a galaxy located at a redshift of z equals 0.55, somewhere around 8 billion light-years away, quite a bit further than the initially calculated distance. The study's lead author Wing-Fai Fong from Northwestern University says that when a pair of neutron stars merge, the most common predicted outcome is that they would form a heavy neutron star, which would then collapse within milliseconds to form a black hole. However, this study shows that it is possible that, for this particular short gamma-ray burst at least, the merged neutron star survived. Instead of collapsing into a black hole, it became a magnetar. As the Hubble observations arrived, the authors realized that they were seeing something quite extraordinary. While most short gamma-ray bursts probably resulted in the creation of a stellar mass black hole, the two neutron stars that merged in this case seem to have combined to form a magnetar. What makes a magnetar so special is its intense magnetic field. This field can be thousands of times stronger than a typical neutron star. These magnetic field lines are anchored into the neutron star and are whipping around at thousands of times per second, producing a highly magnetized wind. The spinning magnetic field lines extract rotational energy from the neutron star formed in the merger and deposit that energy into the ejector from the blast, causing the material to glow extremely brightly. Fong says most magnetars are thought to be formed in the explosive deaths of massive stars, leaving these highly magnetized neutron stars behind. However, it now seems possible that a small fraction are formed in neutron star mergers. But science has never seen evidence of this before, let alone the intense infrared light, making this discovery very special. Kilonovae, which are typically 1,000 times brighter than a classical nova, are expected to accompany short gamma-ray bursts. Unique to the merger of two compact objects, kilonovae actually glow from the radioactive decay of heavy elements ejected during the merger, with some theories suggesting they produced elements like gold and uranium. But scientists have only ever had one confirmed and well-studied example of a kilonova before this discovery, so it's especially exciting for astronomers to find this new potential kilonova which looks so different. The discovery gives scientists the opportunity to explore the diversity of kilonovae and their remnant objects. If the unexpected brightness seen by Hubble came from the magnetar that deposited the energy into the kilonova material, then within a few years this ejected material from the burst should produce light that shows up in radio wavelengths. And so follow-up radio observations could ultimately prove whether this was indeed a magnetar, leading to an explanation for the origin of such objects. This is SpaceTime. Still to come, a new way of seeing invisible dark matter, and a record close shave as an asteroid skims past the Earth. All that and more still to come on SpaceTime.
Hello, Saver. Whether you're saving for that trip to the tropics or saving for an emergency, now is the time to take advantage of Wells Fargo's savings options. Wells Fargo offers savings accounts that can help you save towards your goals. So, what are you saving for? Visit a Wells Fargo branch or wellsfargo.com/save to open a savings account today.
Wells Fargo Bank, N.A., member FDIC.
Astronomers have found a new way to estimate the amount of mysterious dark matter contained in the halos around galaxies. The new technique, reported in the monthly notices of the Royal Astronomical Society, is thought to be some 10 times more precise than the previous best method. Dark matter is a mysterious, invisible substance that makes up an estimated 85% of all the matter in the universe. The problem is, although there's a lot of it, scientists have no idea what it is. But they know it exists because they can see its gravitational influence on normal, so-called baryonic matter. That's the stuff that makes up the atoms that form stars, planets, asteroids, buildings, cars, people, dogs and cats. And dark matter is important because without the added gravitational force of dark matter, galaxies would fly apart as they rotate. Because dark matter can't be observed directly because it doesn't interact with light the way normal matter does, astronomers need to use indirect methods to study it, such as its gravitational influence on the surrounding space. The study's lead author, Paul Gurry from Swinburne University, says it's a bit like looking at a flag to try and work out how much wind there is. You can't actually see the wind, but the flag's motion tells you how strongly the wind's blowing. This new research focuses on an effect known as weak gravitational lensing, which was predicted through Albert Einstein's general theory of relativity. General relativity describes how the mass of an object affects and distorts the fabric of space-time, an effect we call gravity. Now, one of the consequences of this gravitational distortion is that it causes light to also bend. This effect, called gravitational lensing, means foreground objects such as stars or galaxies can be used as lenses to magnify more distant background objects. The study's co-author, Associate Professor Edward Taylor, also from Swinburne, says dark matter causes very slight distortions to the image of anything behind it. The effect's a little bit like reading a newspaper through the base of a wine glass. Weak gravitational lensing is already being used to map the dark matter content of the universe. But what the Swinburne team have done is use the Australian National University's 2.3-metre telescope at the Siding Spring Observatory in far western New South Wales to map how gravitational lens galaxies are rotating. Now, because astronomers know how stars and gas are supposed to move inside a galaxy, they've got a pretty good idea of what a galaxy should look like. And by measuring how distorted the galaxy actually appears, the authors can determine how much dark matter it would take to explain what they're seeing. Taylor says the new research shows how this velocity information enables a much more precise measurement of the lensing effect than using shape alone. He says it provides a clearer picture of where the dark matter is and what role it plays in how galaxies form.
This is an idea that a couple people threw out maybe 10 or so years ago, basically as, hey, this is, a neat idea. This is something we thought of that can maybe work. But it seems kind of totally impractical because the telescopes that would let you do this just don't exist yet. So it's this would be a really neat science application for these future telescopes that are coming online, and especially the Square Kilometre Array, which is a big radio telescope that's being built in Western Australia and Southern Africa. So about 5 or 6 years ago, I realized that actually this idea, which had been thrown out in the context of radio astronomy, was actually probably something that we could do in the optical. Now, it's a really big deal because there are a lot of really large projects that are setting out to do these kinds of dark matter experiments. The Americans have a satellite called WFIRST. It's now called the Nancy Roman Space Telescope. It's a crazy expensive project. It's of order $1 billion US.
Yeah, well, luckily they got the satellite for free from the CIA. Well, not the CIA,
yeah,
the National Reconnaissance Office. But
I'm never sure whether to tell that story or not, but
I don't think
if someone turns around and says, hey, we've got 10 spare space telescopes. Do you want one?
I know
what the answer is.
And you wonder what the difference between the keyhole block 5 and the keyhole block 6 are.
Exactly.
Because redundant.
Exactly. If you've got 10 to give away, that means you've got a couple up your sleeve. So I guess the point is, when this opportunity came along, the thing that they thought would be best to do with this is some of this dark matter science. And the European Space Agency, have a similar project that I think it's a bit cheaper. It's like 800 million euro or something, but it's doing the same sort of thing, and it's called Euclid. So this is like really high profile, this is big astronomy, right? I believe Euclid starts operations in 2 years or so.
Okay.
The way that those experiments work is they go out and they measure the shapes of literally hundreds of millions, billions of galaxies. And if you have that many of them, then you really don't care knowing exactly how far away they are, because you can do a whole lot of this stuff statistically. And so just by mapping this large pieces of sky, you can, by sheer weight of numbers, by sheer weight of statistics, you can kind of dig out this really, really, really subtle signature of the dark matter, this weak lensing signature, which is just this tiny, almost imperceptible distortion in the image of something seen at a really great distance.
What are you actually seeing? A distortion in space-time itself affecting background objects?
So this gets described in a bunch of different ways. So sometimes people talk about it as like Einstein's telescope is what they use, because general relativity says that space-time can be curved in the presence of matter. Right? So if you have something that's really massive, it will, to a greater or lesser degree, curve the space around it. So if you have a big object and you fire some light in the vicinity of that object, near that object, then the light will travel a straight path through that curved space. So if you could kind of step outside space and time, you would see that as the light being deflected just a little bit by the action of that gravitational field. But within general relativity, the way that's described is the light traveling a straight line through curved space. In any case, that apparent deflection is analogous to what happens in a lens. What a lens does is it curves the light as it passes through it. And so in that sense, individual galaxies, and especially big galaxy clusters, by virtue of their large mass, operate a little bit analogously to a lens. And so we use the term gravitational lensing. And one way that this is used is you can use clusters as an Einsteinian telescope, is the way they put it. And what it means is if you have a bright, if you have a massive galaxy cluster half the universe ago, then it magnifies the light from anything that's behind it, and especially the stuff in the very, very early universe. So it's a way that you can actually get some additional magnification beyond your ordinary telescope. That's what's meant by Einstein's telescope. But the trouble is it's a pretty crappy telescope because it doesn't just do the magnification, it also does this distortion. And what the distortion looks like is it's a bit of a bendy, stretchy, squashy kind of thing, so that the image of a galaxy gets stretched in one direction and squashed in the other direction. So if it's a circle, it ends up looking a bit like an ellipse. And as the effect gets stronger and stronger and stronger, not only does it get stretched out into an ellipse, it starts getting stretched out into a bendy ellipse. And then when it gets really strong, it gets pulled into what's called an Einstein ring. And that's what defines the difference between weak lensing and strong lensing.
Right.
So here's the trick, right? So I said before, if the galaxy is a circle, then it gets sort of turned into an ellipse. But galaxies usually look like ellipses, right? Galaxies sort of, they never look like circles. They're always kind of, if you think of a plate, it looks like a circle if you look face on, or it looks more like a line if you look at it edge on. And you can do it anywhere in between. You can make it basically any kind of ellipticity, any axis ratio is the technical term that you like. The trouble is when you're looking at a galaxy, you don't know whether it's sort of elliptical-ish because of how you're looking at it or because of lensing. So the key is if you knew what it would have looked like or should look like, then you can use how it does look to tell you what's happened to it. So the only way to measure this distortion is if you had some good preconception, some well-founded preconception, or some good way of predicting what it should look like. And that's the piece of information that lets you go from what it does look like to what's happened to it, as the difference between what it does look like and what it should look like.
So from there...
So it's like a funhouse mirror, right?
Yeah.
You don't know how tall I am, really. And so if you took my picture in a funhouse mirror, you don't know how much of that is the mirror and how much of that is me. If I was standing next to a ruler, then you'd know how tall I was and how much the mirror was messing things up. I haven't tried using that analogy before, but I don't know if it helps.
It works, yeah.
Cool. So I need to explain the idea of redshift. So redshift is when the wavelength of light that you're looking at is a bit different to what you expect it to be. There's the cosmological redshift, which comes from the universe expanding, and that's not exactly what I'm talking about here. What I'm talking about really is more like the Doppler effect, the ambulance effect, where
this is the
if an ambulance
siren,
is exactly, and it goes nino, 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 like that.
You did that very well. You could get a job in special effects.
If you look at a galaxy that's rotating, so go back to imagining your plate, but it's spinning. One side of that will be spinning towards you, and so it'll be nino, nino, and one side will be spinning away from you, so it'll be nino, nino. If you look in the spectrum, you can figure out how it's spinning. And the point is that information about how it's spinning actually tells you what the shape should look like, because...
So that's your ruler in the fun mirror.
Yeah, except it's not so much a ruler as it is like a bit of graph paper, right?
Yep.
So it doesn't tell you the size of the cell, but it tells you what a right angle should look like, because you've got the bits that are moving towards you and away from you from the plate, and then you've got the bits that are moving directly across your line of sight. So this would be the part of the plate that's closest to you and the part of the plate that's furthest away from you. And you don't see the effect in the stuff that's moving across your line of sight. It just sounds like an ordinary ambulance. So you can draw a line where there's no velocity, and that goes maybe up and down. And then you can draw a line across the maximum velocity, and that gives you maybe a left-right. And so that lets you set up these axes that tell you how the rotation is, and that should be, for a well-behaved galaxy that's rotating properly, those should be at right angles to each other. And when they're lensed, if you look at it in the right way, if you get the right geometry and everything's just right, what that does, it just twists your arms a little bit. So instead of being perpendicular, instead of those axes being at right angles, they're just a little bit twisted. And so what we've done is to use this, it's a I don't want to call it a dinky telescope because I love this telescope. It's so cool, but it's really good at making exactly the kinds of measurements we need for this experiment, which is to measure the rotation of the stars, which lets us set up this axis where we know what galaxies really should look like. We know they really should be at right angles. And so when we see that they're not, we know that it's lensing that did it.
Knowing what shape the galaxy should be, how does that help you to find the amount of dark matter in that galaxy or in the halo of that galaxy?
It doesn't tell you how much is in that galaxy. What we're doing is we're using the light from that galaxy as kind of test particles to fire through the gravitational field of the other galaxy, the target galaxy, the galaxy that's doing the lensing. Are you with me?
Yeah, which is the galaxy in front of it.
Exactly. And so by looking at the distortion, once we figure out how much distortion there is, we can say the reason that that's distorted is because of the action of the lensing galaxy, nearby galaxy. And that lets us say how much dark matter is inside that galaxy that's doing the lensing.
That's Associate Professor Edward Taylor from Swinburne University. And this is SpaceTime. I'm Stuart Gary. Still to come, another asteroid skims past the Earth, this one setting a new record for a close shave. And later in the science report, growing fears that climate change has now reached a point of no return. All that and more still to come on SpaceTime. Well, just in case you thought 2020 couldn't get any worse, an asteroid the size of a house has just swept over the Earth at a record close distance, passing less than 400 kilometres above the South Pacific Ocean near the Pitcairn Islands. Now, to put that in perspective, that's the same altitude as the International Space Station orbits. Luckily, the space station was over the Atlantic Ocean at the time, and it's far lower than the orbit of the Hubble Space Telescope. The ultra-close flyby, which appropriately happened on Friday the 13th of November, wasn't detected until 15 hours after the event. The asteroid, which has been catalogued as 2020 VT4, was only noticed as it was leaving, picked up by ATLAS, the Asteroid Terrestrial Impact Last Alert System at the Mauna Loa Observatory in Hawaii. Not picking up the asteroid until after it's already left isn't uncommon for fast-moving asteroids flying towards the Earth from the direction of the Sun, making them hard to see. It's sort of like a cosmic blind spot. This ultra-close flyby sets a new record for the closest documented non-impacting asteroid pass of the Earth. And it's the second time that this same record has been broken this year. Back on August the 16th, asteroid 2020 QG passed 3,000 kilometres above the Earth's surface, and we thought that was close. 2020 VT4's close encounter with Earth substantially altered the asteroid's orbit. It was on a 549-day orbit around the Sun, inclined at 13 degrees relative to the ecliptic. That's the imaginary plane around the Sun upon which the planets orbit. But its encounter with Earth's gravity well changed that into a 315-day orbit inclined at 10.2 degrees, in the process moving its perihelion inside the orbit of Venus, meaning its next encounter with Earth will be at a somewhat safer distance of around 3 million kilometres, and it won't happen until November the 13th, 2052. And for the record, that'll be a Wednesday. This is SpaceTime.
Wells Fargo presents one of the surest ways to grow your money. A Wells Fargo CD account, where you can earn a 5.00% annual percentage yield on an 11-month term with a minimum opening deposit of $5,000. Visit a Wells Fargo branch or wellsfargo.com/CD rates to open a CD account and start growing your savings with us.
Wells Fargo Bank, N.A., member FDIC.
And time now to take a brief look at some of the other stories making news in science this week with a science report. US biotech company Moderna claims ongoing phase 3 trials are indicating that its RNA-based vaccine will be more than 94.5% effective at preventing the COVID-19 coronavirus. The results, which have not yet been peer-reviewed, are based on 95 confirmed cases of COVID-19 among 30,000 participants, with 90 cases occurring in the placebo group and 5 in the vaccine group. It's the third time this week that a COVID-19 vaccine developer has reported preliminary results suggesting its vaccine is highly effective. Pfizer initially claimed their vaccine was 90% effective in preliminary Phase 3 trial data, but as more results have come in, they've now upgraded that to 95%. And then there's the controversial Russian vaccine Sputnik V, whose proponents have declared it to be 92% effective against the coronavirus. However, both the Sputnik and the Pfizer data is also still preliminary, with neither having been peer-reviewed, and in the case of Sputnik, many questions are yet to be answered. Like the Pfizer vaccine, Moderna's was developed as part of President Donald Trump's Warp Speed project, designed to accelerate COVID-19 drug development. Also, like Pfizer, it'll require 2 jabs several weeks apart. But there is a big difference. It'll remain stable in conventional refrigerators for up to a month and in ordinary freezers for 6 months, as opposed to the Pfizer vaccine, which needs to be stored at minus 70 to 80 degrees Celsius. Meanwhile, Phase 1 trials for the University of Queensland's COVID-19 vaccine are also showing it to be safe and effective, producing virus-neutralising antibodies, and it appears to be especially effective in elderly trial participants. The new molecular clamp vaccine binds together synthetic surface proteins from the SARS-CoV-2 virus in a form that appears to generate a strong antibody response. If ongoing trials prove successful, it'll be manufactured in Australia by CSL, with the federal government committing to purchase 51 million doses. The COVID-19 coronavirus has now killed almost 1.5 million people and infected some 57 million others since first spreading out of Wuhan, China, a year ago. The United States Senate Judiciary Committee has confirmed that Facebook, Google and Twitter are engaged in a coordinated campaign of political suppression and censorship. Under questioning by Senator Josh Hawley, Facebook chief Mark Zuckerberg admitted the existence of a coordination program, but he claimed he wasn't personally familiar with its exact details. Evidence about the coordinated suppression and censorship campaign were first revealed to the Missouri senator by a whistleblower working at Facebook. Meanwhile, during the same hearings, Twitter boss Jack Dorsey was forced to admit that his company had suppressed or censored more than 300,000 political tweets. The evidence supports growing fears that tech oligarchs are engaged in controlling what you're allowed to see on social media based on the tech giant's own political views. Social media sites including Facebook, Twitter and YouTube, as well as Google, dramatically increased their political censorship leading up to the 2020 US presidential election. There are growing fears today that climate change has now reached a point of no return. New climate modelling suggests that even ceasing all greenhouse gas emissions now might not be enough to stop global warming. The reduced complexity model suggests that even with no further emissions, global temperatures will still rise enough for Arctic ice and permafrost to continue melting and thawing for hundreds of years, releasing their stored greenhouse gases into the atmosphere and reducing the amount of sunlight reflected away from the Earth. Researchers say at least 33 gigatons of carbon dioxide needs to be removed from the atmosphere annually from 2020 in order to limit the worst effects of climate change. You can read that study in full and all its depressing findings in the journal Scientific Reports. Scientists have for the first time sighted the elusive big-fin squid in the waters of the Great Australian Bight. It's the first time these rare squids have been found in Australian waters and one of only a dozen confirmed sightings globally. The squid, which have extremely long arms and tentacles, were filmed at depths of 2 to 3 kilometres during a program of deep-sea survey voyages led by the CSIRO. A report in the journal PLOS ONE claims 5 big-fin squid were seen and filmed during 2 separate voyages. Scientists measured one of the squid at over 1.8 metres in length and also observed what they describe as unusual squid behaviour. A new study has tried to get a handle on the sorts of personality types that are more prone to conspiracy theories and outlandish beliefs. Scientists found that the personality traits solidly linked to conspiracy beliefs included some unsurprising types, such as people who felt entitlement, self-centered impulsivity, cold-heartedness, the so-called confident injustice collector, as well as people with elevated levels of depressive moods and anxiousness. But as Tim Mendham from Australian Skeptics found, the study also uncovered another personality disorder associated with a specific pattern of thinking.
There's a continuum as to how dangerous people who follow conspiracy theories are. Some of them are just sort of amusing, and some of them take it to extremes. Obviously, terrorists are normally underlined by strong conspiracy theories, and certainly white supremacist movements and that sort of thing are generally highly regarded as conspiracy movements and extremely dangerous, become basically terrorist movements. This was a study that was looking at the sort of people who would believe in conspiracies, and there's a high percentage, this is in the US, a high percentage of people, they suggest that of Americans who firmly believe at least one conspiracy theory, and they call them discredited conspiracy theories, so anyone who believes at least one would be about 50% of the population. Obviously, there are some who believe more than one, and there are some who think it's all garbage, and therefore they looked at the sort of people, they did two surveys. One was asking what sort of beliefs you have, a separate survey of the same people, but going back to them with a different sort of study was what sort of personal, emotional characteristics do you have? And obviously a lot of this is self-descriptive, so they asked the leading questions that such surveys have. And the interesting thing was some of it not that surprising. Some of these surveys you look at end up stating the obvious, at least they're saying it, and they can sort of say it's scientifically based rather than your necessarily assumptions that you have. So they're putting some numbers to the assumptions. But the typical person who believes in conspiracy theories, people tend to be a mixture of characteristics. Some people are self-centered, entitled, they believe they should have things. This is often someone who believes that they see injustice everywhere and they are right to fight it, even if the injustice is in their own head or within a groupthink. You would quite frankly say that some social justice warriors would fall in there. Some wouldn't. Some would have some quite justified complaints and issues. Others tend to see it everywhere, injustice everywhere, and therefore if they believe that I'm entitled to a particular set of circumstances and I'm not getting it, therefore they see a conspiracy as to why they're not getting it.
It's there are other people. The man's doing it to me.
Them. Yeah, they're after me. The other one is obviously people who are depressed or anxious. They might be confined for whatever particular reason or circumstance. They're sort of down in the dumps, and therefore they worry about such things, and therefore they try and find some reason why they're depressed, or they just see it. Other things that are sort of, there are personality disorders that some people have, which is sort of on the sort of psychosis levels, including one which is called psychoticism, which is a schizotypal, they call it, personality disorder characterized by odd beliefs and magical thinking. Paranoia obviously comes in there a lot, comes in with a lot of these people. That's why they believe that they're out to get you. And the conspiracies become popular.
With so many people being locked down because of the current coronavirus pandemic, does that increase or decrease the rate of conspiracy thinking?
Generally speaking, it actually almost like it polarizes people.
Oh.
And in that survey, that they said about 50% of people believe in at least one conspiracy. That means 50% of people don't. Okay, that's on the positive side. So therefore, with something like a coronavirus, if the regulations are explained rationally, people can see a reason for them. They might not like them, but they can see a reason for them. If you are a person who has certain characteristics that make you lean towards conspiracy theories, you will find a reason why those regulations are coming in, apart from the obvious health ones. So it does polarize people. Those people who have a tendency to believe conspiracy theories might be more encouraged by the impost of regulations upon them. But those who perhaps don't have it necessarily, first resort is to think of a conspiracy theory, would tend to go towards I understand this, there's a good reason for it, I don't like it, but I will accept it and abide by it. So that's why you get these sort of conflicts of people out there campaigning, I want to wear a mask, I shouldn't be locked down, I should be able to go and meet with whoever I like. And they totally ignore the health and the science, because that's the reason those regulations are there, not just to force people to wear masks.
What about the people being stuck at home because of lockdowns, having more time to think and ponder things? Is that likely to increase the rate of conspiratorial thinking, generally, not just about things to do with COVID-19?
All of these things rely on your propensity to believe. Yes, you're given more opportunity to go online and Google your way through all the conspiracy theories and discover stuff, to read emails from people who may have conspiracy theories and saying, you should be aware of this. Whereas in your normal unlocked down life, you might have less time for that. But I think also it's tempered by your propensity to believe. If you don't believe in conspiracy theories and you see someone who's madly promoting them avidly, you might start wondering about them more than the conspiracy theory. If George comes to you, right, or comes to me and says, you've got to know this, you've got to know that, you've got to know this. I'm not necessarily going to be more inclined to believe George that time than I am at any other time. But you're probably right. There's certainly more opportunity to be exposed to this stuff. But it doesn't take a lot of exposure for people to believe conspiracy theories. It just reinforces the conspiracy. Some people hear a conspiracy once, that's enough, and then every other time they hear the same thing over and over again from different sources who are just repeating the same stuff and copying each other, that just reinforces it. It doesn't set up the belief in the first place.
That's Tim Mindham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more space time, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.
Wells Fargo presents one of the surest ways to grow your money. A Wells Fargo CD account, where you can earn a 5.00% annual percentage yield on an 11-month term with a minimum opening deposit of $5,000. Visit a Wells Fargo branch or wellsfargo.com/CD rates to open a CD account and start growing your savings with us.
Wells Fargo Bank, N.A., member FDIC.
Hello, saver. Whether you're saving for that trip to the tropics or saving for an emergency, now is the time to take advantage of Wells Fargo's savings options. Wells Fargo offers savings accounts that can help you save towards your goals. So, what are you saving for? Visit a Wells Fargo branch or wellsfargo.com/save to open a savings account today.
Wells Fargo Bank, N.A., member FDIC.